Evolution is defined as a change in allele frequency in a population over generations. Let's talk about populations. In this lecture, I'd like you to be able to define population, gene pool, Hardy-Weinberg equilibrium, genetic structure, and genetic drift. Write the Hardy-Weinberg equation and define all terms therein. Calculate genotype frequencies and predict genotype frequencies. So calculated and predicted are going to be different things, and to compare these two things, I'd like you to use a chi-square test to see if evolution has occurred, if there has indeed been a change in the allele frequency over generations. You may note that today I'm not wearing a button-up shirt. That's because I got this manila gorilla shirt and I absolutely love it. So, what is a population? Well, a population, let's see, populations, a population. It's a group of organisms of the same species, living at the same time, and in the same place, and capable of interbreeding. So essentially we're defining a population as a large gene pool and the organisms that represent it. So this large crowd of people is a population. It's actually probably just part of the population. If that was, say, if that was a large crowd in Mumbai, then that would just be a small percentage of the total number of people in Mumbai, which would be a small bit of the population of Mumbai and surrounding suburbs that would make up the population of people there. We also have a gene pool. So what is a gene pool? Well, I want you to imagine for a moment a species of frog. Now this species of frog, or this population of frog rather, they all go to the same puddle, and they're all going to deposit their sperm and eggs in that puddle so that those sperm and eggs can intermingle and form zygotes, which will form the next generation of frogs. In that case, what you have are all the gametes are going to be gathered in one area at one time. So all the mating is occurring in one area at one time. And now that puddle is quite literally a gene pool, containing all alleles for all genes and all possible combinations therein are in that one pool. We're often looking at a gene pool for just one gene. Because if we're saying like the P's and Q's and the big A's and little A's, well, that's just one gene, two alleles for one gene. If related to a population, all alleles in that population are the gene pool. So one way to figure out the gene pool and how things would go is you look at this figure here and you point around and you select an egg. And if it's in uppercase A, then you go around and you select a sperm. And it might be an uppercase A, and that's going to make an individual, if those were to fuse, of homozygous dominant. So you can basically pick out those and you can see the probability. And that is the lengthy way of doing things, to basically look at all the probabilities, do it 100 times and calculate what percentage of the time you get homozygous dominant, what percentage of the time you get homozygous recessive, and of course what percentage of the time you get a heterozygote. So you can look at the gene pool that way, or we can look at it in terms of allele and genotype frequencies. Your allele frequencies, if you were to go back to that gene pool and you were to look at how many uppercase A's there are out of the total number of sperm and egg, that is going to be the number of copies of a specific allele, uppercase A, divided by the total number of all alleles for that gene and population, the total number of gametes there. And that is your actual allele frequency when measured properly. If you actually take out all the copies for an allele, genotype the whole population, you're going to get the allele frequency. Your actual genotype frequency is the number of individuals that come out of that gene pool that are going to have homozygous dominant, heterozygous, or homozygous recessive. So the number of individuals expressing each one of those genotypes out of the total number of individuals in the population is your actual genotype frequency. So how is this calculated? Well, quite literally just count them all. You know, gotta count them all, gotta count them all. It's very time consuming, and it's unlikely that you will ever actually be using that to calculate allele frequency or genotype frequency. Rather, you will take a subset of the population and you will calculate from that. So here's an example. We have the allele frequencies and the genotype frequencies. So your allele frequencies here, I erase it 5 times quicker with Windex, but it makes it hard to write. Okay, so the frequency, we can look at how many of eggs and spermies are going to equal, we have this kind of genotype. So if we know that this is 0.6 and we know this is 0.6, the probability of getting one of each of those is going to be 0.6 times 0.6, or equal to 0.36. So that's the probability of the homozygous dominant, is the probability of getting an uppercase A and an uppercase A. Now that's also going to include the uppercase A. Actually, that's just both of them. They can't occur. You have the egg and the little sperm, or the egg plus little spermy. You have two different ways of getting that. So you have remember this is 0.6 and this is going to be 0.4. So that's going to be equal to 0.6 times 0.4, or 0.24. You're going to add those together, because both of those possibilities, to get 0.48. And then we have this, which is 0.4 times 0.4. Some zeros up there. And that's your 0.16. So that's how we're actually going to be getting these different allele frequencies to make these different genotype frequencies. We can see the allele frequencies of 0.6 and 0.4 yield genotype frequencies of 0.36, 0.48, and 0.16. This should sound like what we did back in Bio 142, but hopefully with this, with your textbook, what you can see is you can actually take that and test it with yourself by taking your finger and just pointing randomly, and if you feel so inclined, do it 100 times and you're going to get these frequencies, or something very similar. So let's show the calculations for these. So if you had a population of mainly, actually we're going to do these and then the calculations. If you had a population that is mainly homozygotes, you have 90 homozygous dominant, 70 homozygous recessive, and only 40 heterozygotes. Let's calculate the genotype frequency. So 90 divided by 200 is going to be 0.45. Your 40 divided by 200 is going to be 0.2. And your 70 divided by 200 is going to be 0.35. So you see the genotype frequencies in each of these. Let's look at the allele frequencies for that. So the allele frequency of your uppercase A, we're going to call that P. So we have, if we're going to make our calculations, we're going to have, of course, our P is going to be our frequency of the uppercase A, and we also have our Q, which is our frequency of A plus frequency of lowercase a, is going to be equal to 1. These have to equal 1. There are only two possibilities. If we looked at the frequency of heads and frequency of tails, we're going to find out those equal 1 together. So let's see, the P is equal to 2 times 90. Hold on, it's math, I know, but let's look at this. That 2 times 90, each one of those 90 individuals, that is homozygous dominant, has 2 copies of the dominant allele. So you get 2 times 90. Each one has 2 of those alleles. Each heterozygote has 1 of those alleles. So 2 times 90 plus 40, divided by 400. Why 400? 2n. The total number of alleles in the population is 2 times the total number of individuals, because each individual has 2 of these alleles. So 2 times 90 plus 40 over 400 is going to equal 220 over 400, equaling 0.55. So the frequency of your uppercase A, we call that frequency P, is going to be 0.55. What about Q? Well, that's going to be, we could just calculate it as 1 minus P, but let's check our math. So 2 times 70, because each of the individuals that is homozygous recessive has 2 copies of the recessive allele. And if you also take 1 copy each for the heterozygote, you're going to see that 40 copies of the heterozygote, 40 copies of the lowercase allele in the heterozygotes exist in your population of 200 individuals with a total of 400 alleles. which is equal to 180 divided by 400, and yes, it is 0.45. You really need to check your math after this to make sure that P plus Q does indeed equal 1, because if it doesn't, you done gone wrong. Alright, so P plus Q plus equals 1. There, check our math. Excellent. Let's look at population 2 a little quicker. There's 60 homozygous dominant, 100 heterozygous, and 40 homozygous recessive in this similar population of 200. 60 divided by 200 is 0.3. 100 divided by 200 is 0.5. And 40 divided by 200 is 0.2. So those are the genotype frequencies of each. But let's look here the frequency of the alleles. You have 60 times 2 because each one of those homozygous dominant individuals has 2 copies of the dominant allele. Plus 100 for the heterozygotes, each have 1 copy of the dominant allele. Divided by 400, total copies of the alleles in the population is going to equal to, 0.55. Let's zoom through this math, and you see 2 times 40 is your number of homozygous recessive individuals with 2 copies of the recessive allele each, plus 100 of your heterozygotes here. Over 400 is, yes, 0.45. And again, you check your work to see that the allele frequencies are the same as the first one and still add up to 1. So it shows that 2 populations can actually have the same allele frequency, but have different genotype frequencies, which is an allele distribution. The genetic structure of a population is defined as the allele frequency and the allele distribution, also known as the genotype frequency. Well, let's look at that genotype frequency. We would use the calculation here, p squared plus 2pq plus q squared equals 1. How we get that is going to be your frequency of A times frequency of A, these uppercase A's, is going to equal your P squared. Your frequency of getting, let's see, this guy first, and this guy second, plus your frequency of getting this guy first, and this guy second. And that's going to equal, this is PQ, QP, multiplication means they're the same thing, and that's going to be 2PQ. And this is your frequency of getting each one of these. And that's how we're going to get our Q squared. So those are the frequencies, and we call this the Hardy-Weinberg equation because it takes all those genotype frequencies and adds them up together to figure out that, yes, all the different possibilities of genotype frequencies equal 1. Because there are only 3 different genotypes an individual can be: homozygous dominant, homozygous recessive, or heterozygous. And that's your genotype frequencies shown out there. The genotype frequency of the homozygous dominant, the heterozygote, and the homozygous recessive. And you can use this to estimate or predict allele and genotype frequencies in a population. This is your predicted. So your actual is when you go and you measure them. Your predicted is when you use this equation, given a known allele frequency, you use this equation to predict what your population would be. But that's really only true if the population is in Hardy-Weinberg equilibrium. Well, is it? Let's test. And thankfully, there is a statistical test that can be utilized to determine if a population is in Hardy-Weinberg equilibrium or not. Why do we care? Well, that's the whole reason for this class. Honestly, we care because when a population is not in Hardy-Weinberg equilibrium, it is evolving. And this class is about evolution. Thus, this class is about populations that have violated Hardy-Weinberg equilibrium. So how do we know when it's not? We use something called the Chisquared Test. That's a chi. It looks like an X, but it's Greek, so it's chi. Some of you may say the chi-squared test. Well, that's just a type of t. So chi-squared test is equal to your observed minus your expected over your squared over your expected. So we're going to take a coin flip example. Each person in the class should have a coin and should flip it. Or you at home, flip a coin 10 times. Your expected is that 0.5 times 10, n equals 10, is going to be heads. So at home, take a coin and flip it 10 times. You can pause me so I don't have to wait. Okay, so what's your observed number of heads? All right, so that's your observed number of heads. let's see, you have your heads and your tails, your observed, and your expected. So your observed number of heads would go here. Let's say you got 7 heads, which means 3 tails. Your expected is 5 and 5. We're then going to take that one step further, and your observed minus expected, we're going to square that. So 7 minus 5 is 2, 2 squared is 4, 3 minus 5 is negative 2, negative 2 squared is 4, and then we're going to take the sum of those observed minus expected, squared, and each of those is going to be divided by the number of expected. So you got 4/5 plus 4/5, that's going to be 0.8 plus 0.8, and the sum of those is going to be 0.8 plus 0.8 equals your chi-squared value of 1.6. And you're going to compare that to something called a chi-squared table. Go for a moment and look up your chi-squared table. You see how there's a p-value on your chi-squared table, and your chi-squared for a given number of samples, in this case 2, and then you're going to, so your degrees of freedom is actually 2 minus 1, so 1. Why? Because you are either a head or a tail. You can't be both, and you have to be one. So given that you were a head, you had 1 degree of freedom, you could have been a tail. If you're rolling a 20-sided dice, there are 19 degrees of freedom, because you could have been 19 other things. So your degrees of freedom is 1 for this test. Your chi-square value is 1.6. And you're going to compare that. This value needs to be bigger than a certain value, because the bigger the difference, the bigger the chi-square value. So I believe for a chi-square of degrees of freedom of 1 and a p-value of 0.05, which is our general taken as significant, I believe chi-square is 3.16. Now I could be wrong on that, I don't have a chi-square in front of me. But is this larger than 3.16? And if so, it is a significant difference. If it's smaller, it is not a significant difference. And what we're intending to see here is if it's a significant difference, then that coin was rigged. So you know the coin was rigged if it's significantly different from the expected values. If a population is significantly different than the expected values, then the population is changing. So if our P's and Q's are significantly different than the expected P's and Q's, we can imply that the population is evolving. That was a bit tough, and I do encourage you to ask questions and to kind of review the chi-squared table and chi-squared test a little bit. We did do it in Bio 142, but you might need a little review because you don't use chi-square every day. Ah, yes, there's a chi-squared table. Forgot to put that in there. Okay, and for 0.05, I was off by a little bit. You can see here your 1 degree of freedom, and your 0.05, it's 3.84. Okay, so 1.6 is smaller than 3.84, so as I was right, it's not significant. Okay, so I'm not going to cover these over in great detail because I want you to calculate these on your own, and I'm just going to kind of go through it very briefly. So your PKU, phenylketonuria, is a 1 in 10,000 thing. So Q squared is getting 2 alleles for that Q, for the PKU genotype. So is equal to that. That's your Q squared. Well, let's figure out what Q is. You take the square root of Q squared to get Q, and that's how frequent the allele is in the population. 1% of all alleles in the population have your PKU alleles. It sounds like a lot until you realize the probability of getting 2, and thus getting phenylketonuria, is going to be very low. What is phenylketonuria? Look it up, and then look up Diet Pepsi. Estimated frequency of normal alleles is going to be, well, P equals 1 minus Q equals 0.99. So we don't have to measure that, we can just look at it this way. Your estimated frequency of carriers is going to be 2 PQ. 0.0198. 2% of the US population are carriers for this allele. So, if you're looking for allele frequencies, remember it's P plus Q equals 1. Genotype frequencies, P squared plus 2PQ plus Q squared equals 1, and carriers are your heterozygotes. You can find Q, and the quickest and easiest way to do this is by finding Q and starting with Q squared, because we often know the frequency of recessive phenotypes. They tend to stand out from the dominants. Take the square root of Q squared to give you Q, and once you know Q, 1 minus Q is P. So example number 1, here we go. Heart nut disease is autosomal recessive. Affected newborns is 1 in 14,000. 1 in 14,000. So frequency of carriers, well, you're looking for 2PQ. I'm going to let you do this on your own and review it on your own. And check your math with this. So your frequency of carriers would be 0.01676. And you can use the PowerPoint slides that I have provided to work this through if you're having any trouble. 1.7% of the population are carriers for this disease. A herd of dairy cattle contains a recessive allele for dwarfism. If the frequency of normals, okay, so we know the dwarfs are 10%. Boom, right there. What's frequency of carriers? So 90% are your p squared plus 2pq. Okay, so that's your dd and dd. That's actually not informative. You're looking for is your q squared, which is 0.1, 10% of the population. So your frequency of the q allele is 0.31. Frequency of normal alleles is 0.6838. Frequency of carriers is your 2pq. So about 43% of the population. Certain grasses, the ability to grow in nickel-contaminated soils is determined by dominant alleles. 60% of seeds are able to germinate. Okay, good. What's the frequency of the resistance allele? So that's the, not recessive, that's resistance. So they can grow. Let's see. So there's your genotype. You're looking, though, for your q squared, remember. Q squared is your NN, your lowercase n's, 0.4. And that's going to be actually a pretty high frequency of that q allele. And your frequency of your resistance alleles is P. All right, so all this to say, we take our frequencies and we're going to look for a population and see if it's going to be in what we call Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium is just simply defined as non-evolving. A population that is non-evolving must meet 5 distinct assumptions. Hardy-Weinberg equilibrium, is a population that is not evolving. We're going to make 5 assumptions. You want to write these down because we will be using these a lot. First off, the population is large. Small populations, as you may have remembered from 142 or other classes, tend to undergo what is genetic drift. So random events are going to cause genetic drift. Genetic drift is when a population randomly has fixing of one of the alleles, which is going to randomly take one of those alleles and change it. So small populations have random fluctuations in their allele frequencies. That's genetic drift. Population is isolated. So there's no migration, no imports or exports of new alleles. There are no net mutations. So there are no new alleles coming in via mutation. Random mating. There isn't some sort of selection where all of these work together and all of these go together. And of course, no natural selection. Equal survival and reproduction. We're going to be spending the next few weeks covering these 5 assumptions because these 5 assumptions, when violated, cause evolution. So, evolution is when one of these or more are not being met. So we assume allele and genotype frequencies stay the same from one generation to the next. That means a static gene pool and similar genetics or same genetic structure. If it's not in equilibrium, it means the population is evolving. A violation of one of the 5 different types of Hardy-Weinberg equilibrium causes microevolution, the change in allele frequencies in a population over generations. So that's what we need to know for Hardy-Weinberg equilibrium moving forward. We're going to want you to double back on some terms that are covered in this first section of things. First off, paralogy versus orthology. This often is something students have a problem with, so it's good to know. Make sure you know the 4 postulates of evolution by natural selection because we will be covering those on the exam. And the 4 types of mutations, your lethal, your deleterious, your neutral, or your beneficial regarding fitness because we will need to build on that structure later, so I will need to put that on the test. Reaction norms is something students often have problems with, and make sure you're caught up on your Hardy-Weinberg equilibrium. These silly little calculations, well, we need to know them, and you need to be able to do them, both for your MCAT and for the next couple of slides. So we're going to have this coming up on the test. However, this is where we'd like to end material for exam 1. So there we are, material up to and over exam 1. You can stop the material here, write a little thing in your notes, end material for exam 1, and for the next lecture, begin material exam 2. Thank you.